All right, let's pray. Heavenly Father, we thank you for this day. I thank you for these students, for a working thermostat in this room. And I just pray that you'd help us to understand more about the Frobenius Method today. Help us again, Lord, to glorify you in what we do. In your name I pray, Lord Jesus. Amen. So as I mentioned, you guys have an extension on the homework till Monday. Apparently series are hard to calculate. Who knew? Who'd thunk it? It's a year. But anyway, I know it's always takes a little time to get back up to speed. I think I'll get this here in a second here. So I'm a little bit sick. Okay, I'm just sick. I mean, there's like no little bit about it. I don't know how I'm sick again. It's really annoying, you know, because like it seems like I just got better. But anyway, it is what it is. So in the interest of being understandable today, I'm going to use the projector. And also, even if I wasn't sick, I might use the projector on this material just because it has just so much opportunity for making a mistake. And we need really precision here. Precision is so important here. Frobenius Method is one of those things where if you're hurrying, you might as well just not do it, frankly. So, here's the problem. So we've got, oh man, I see I should have gotten my glasses. Aha! I was worried they were in my other bag. Okay, so we're going to consider y prime prime plus py plus q with a regular singular point x naught. First of all, I want to point out to you that if we can make this substitution, x equals t minus a, what's that do? If I plug in x equals t minus a, x squared becomes what? It becomes t minus a squared. X becomes what? Yeah, t minus a, and I should really have a. I mean, I'm missing a p and a q down here, guys. The point is, you do p of t minus a and q of t minus a. All right, and then the dz dt. I mean, how are the derivatives of x and t related? If a is a constant, well, dx dt is equal to. dy dt, dy dx is equal to dy dt with the arguments appropriately shifted. The point is, you can change this differential equation to that differential equation. You can do the same with p's and q's. So there's really no loss of generality in assuming that we're at the zero. Because if we're not at zero, we can always shift it to be a zero problem, solve that problem, and then shift back. It's a standard technique. I will give you a homework problem where you actually get to do that for a specific a, most likely. Okay. If you do it once, then you can understand it. But you don't really understand it until you do the homework problem. I mean, you believe what I said because everybody believes that dy dx is equal to dy dt because, it's just chain rule and dx dt is just equal to 1. So, but anyway. All right, so here we go. This is then, in that sense, general. Y prime prime plus py prime plus qy equal to 0, a singular differential equation at x equal to 0, and it's a regular singular. In other words, if I multiply this by, p and q can have, p and q are not analytic at 0, but their fall from analyticity is relatively mild because if I multiply p by x, I get a power series, right? If I multiply this by x, I get xp is equal to p naught plus p1x plus p2x cubed and so forth, right? If I multiply this by x squared, I get x squared q is a power series. So yeah, p and q are singular at 0, but they're mild in their singularity. So this is a regular singular point, as I defined last time. And we want to solve this problem, all right? So this is what Frobenius Method says. It says you can solve this kind of problem. At least here's one solution. At a regular singular point, this problem has a solution of the form some coefficients, some real numbers, or, we'll let them be complex numbers eventually. I mean, honestly, so we again run into some algebraic condition on R, and it could be that R ends up being complex. In the case that R ends up being complex, that forces us to entertain the possibility that the A sub n are also complex coefficients, much like we've done before. We make a general algebraic guess on what the solution looks like, and if the algebra leads us to a complex characteristic value, then we're forced to entertain like a complex solution, and then we pick off real and imaginary components to get the two real solutions from that. Same thing happens here, just like in our previous work. And okay, anyway, so let's keep it real for a little bit, because none of this algebra changes when R is complex. Okay, the analysis is still the same. The derivative of y, you differentiate component-wise. What's the derivative of x to the n plus r? It's n plus r times x to the n plus r minus 1, right? And what did I do? There's one huge step I made here, a very bigly calculation, if you will. Oh, I'm sorry. Are you with her? No? You guys look like Johnson supporters, maybe. I don't know. You're not going to tell me, are you? I mean, you don't have to. Are you for the meteor? I mean, I've heard students tell me they're for the meteor. I don't know. My brother told his class, he's like, you know, I think about a candidate running, and I just think, you know, they're so corrupt, and how can I vote for this person with all this corruption and all these scandals? And then I think, the other candidate, though, has all the same corruption and all the same scandals. So, and I think it's funny how he found a way to make a comment about the election, which was completely, like, everyone hears this comment. Whether you're in one party or the other, or actually any of the four parties that we're currently entertaining, really. It probably makes sense about the other three candidates. And I don't know, I guess there's no controversy with Johnson, per se. I don't know. I digress. Obviously. Let's see here. So the point is, I'm putting the derivative from outside the sum to inside the sum, right? And that's a huge step. Like that, there's a lot of analysis that's required to prove that. And I haven't shown that that's true in these notes, and I'm not going to, because this is not an analysis class. It's a differential equations class. But it is. You should understand that there's some significant mathematical work that has to go into proving this is a legitimate step. All right? And I haven't done that, and I'm not going to do that. But you believe me when I tell you the derivative of y is just component-wise differentiation, right? Intuitively, it's a reasonable step, right? And likewise, when you twice differentiate, see, I'm just doing what you guys are already doing in the homework on power series, right? It's just now r is not necessarily an integer, okay? And then I just plug these into the differential equation we're trying to solve, right? I've got x squared times y prime prime, and then I've got x times p. This is x times p, right? Times y prime. You guys with me so far? Then what comes next? X squared, right? X squared times q, right here, times y itself, which is just the raw Frobenius solution. All right. Then what happens? Well, collect things together, right? So what am I doing? I'm multiplying. What did I do there? Let's go back up here. What did I do? I just multiply this x squared inside, right? So that just changes this to an x to the n plus r. It doesn't change any of this, right? Oh, no. Sorry. I will try not to infect you guys. Although my children recovered from this cold already. I still have to work my way to a cough, which I won't recover from for a month. Once I'm done with that, then I'll be back to normal. That's what I'm anticipating. So, anyway, this one, on the other hand, well, I can move the x over here, right? And that will give me an x to the n plus r. Here, there's nothing to move. And then we'll have x to the n plus r, x to the n plus r, x to the n plus r, and all of them, right? Yeah. And this is, you know, this is about as clean as it gets. There's really nothing gained, as far as I see, at the moment. I mean, to be honest, if you really want to get into this more deeply and really become a calculational master at this, you should study Rabenstein. He has a few more tricks than I show here. But this will suffice for our purposes. So like that's about as clean as it gets. So I'm going to leave it right there. All right, that's going to suffice to look at order by order, collect terms. So first of all, you look at here, and the point is that this x to the r plus 1, x to the r plus 2, this is a linearly independent set of functions on the appropriate interval. We're going to call the generic Frobenius solution y of rx. So like y of rx is exactly this thing. All right, that's our proposal. This is the y of rx right here, just that. All right. Anyways, to get this to be 0, we have to have the coefficient of x to the r plus 1, and so forth and so on, all of those to be 0, right? If we've got this combination to be 0, it has to be holding for all x in some interval. It must be that each of the coefficients of each order vanishes. Okay, does that make sense? So the n equals 0 terms, how do you get n equals 0 here? In other words, how do you get x to the r from all this? Well, so if we look at this, when we put n equals to 0, we get x to the r here, right? We get what? A sub 0 times r minus 1. That's where this comes from, right? So these terms right here are from plugging n equals to 0 into that. If I plug n equals to 0 into the next thing, I get what? I get r times a sub 0, right? And then p sub 0, so I get this term, right? And then I, oh no. But also, right, well, is there anything else? No, I guess I can't get, if I have the x here, I can't get back to, that doesn't, I mean, x times this doesn't give me back it gives me an x to the 1 plus r, right, but it doesn't give me back an x to the r. The only way to get x to the r is from putting n equals to 0 here and multiplying by the constant term, right? So that's this one. And then down here, it's just q naught times a sub 0 x to the r. So then I'm just peeling off the coefficient of x to the r. It's exactly this, all right? So this should be somewhat familiar. We've already seen this already. It is the characteristic equation for the Cauchy Euler problem in the context that p and q are just constants. Yeah? Mm-hmm.
Third term of p, so that's supposed to be x, p sub 2, x to the third.
Oh, that's supposed to be an x squared. I think I have gotten, oh man, look at that. Sad, 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 sad. Yeah, that should be an x squared. You see what I did is I left it out here, but then I mean, it's double counting. Yes, that should be an x squared. Thank you. Yes, 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 yes. Oh man. Well, that's just hideous. Sorry. Anyway, this thing has a name. This equation, once you clean it up and drop the zeros, right, you can rewrite it as r times r minus. Again, really? Oh, there's an a naught. I'm sorry. There's an a naught in everything here. I was about to say, where's my a naught? Oh, I'm an idiot. There's an a naught here. There's an a naught here. There's an a naught here. Right? So it implies then that we should have whatever's left be equal to 0 if we don't want a sub naught to be 0. We don't. So that forces us to have this condition on r. This is called the indicial equation because it sets the index. R is the index, okay, for the solution. All right. So I could skip ahead and show you how to solve the indicial equation for a particular problem, but I'm not going to do that. We'll get to it. We'll have a specific numerical example here before too long. Let me just finish running through the general setup. Keep it in order here. So this is the beginning of the Frobenius problem, is to solve the indicial equation. That tells us what to set r to. All right. Now, it's kind of fun to just go ahead and, I think, so I've gone through a couple of stages in my calculational development of this method. I think what I used to do is I used to find r and plug it in as soon as I found it, right? But I don't think this is wise. It's actually smarter to kind of work out these, like this general, well, I'm not sure. Now I can't remember. Was it better? this is a question, right? Is it better to plug in r as soon as you know it and then work with it? Or is it better to leave r symbolic like this? Let's keep that question in mind. We'll decide here together as we go on which is the wiser choice. Here I haven't, I mean, this is just a generic discussion, right? So here's like the coefficient of x to the r plus 1. So I go back to the star equation. This thing does have an up-down scroller, but I actually have to plug in the USB thing to make it work. Now I'm regretting not doing that. I paid $6 whole for this. Let's see here. Thank you, China. Or should I say China? Let's see here. The way he says China is just, it's not right. But anyway, so the point is, to get x to the r, we put a 1 here, right? 1 plus r, and then times r, right? Because 1 minus 1 is 1. And then to get x to the r here, I can either do p naught times a1, 1 plus r, right? Or I can do p1 times a sub naught times r, right? And then to get x to the 1 plus r down here, I do q1 times a naught, or I do q naught times a1. So then you start picking up these things from the Cauchy product. You got to think about, how can I assemble x to the 1 plus r? Well, there's more than one way, right? So that's what's down here. So you see, you get all these. You pick up more than just the a sub naught. You pick up the a sub 1 and the a sub naught, and they're intertwined by the x to the r plus 1 term. And if you keep doing this, the x to the r plus 2 would be this, right? So that's about as far as I want to go for the general thing. And I'm not suggesting you should use these equations to plug in r. My point is just that this is the idea, all right? Like I said, for given problems, the recurrence relations which define the a sub k are best derived directly from star. I'm just trying to indicate the general pattern. All right, so here we go. A specific example. Get that cursor off there. Oh no. Oh no. All right. So 3x y prime prime plus y prime minus y is a regular singular problem. It's pretty nice actually. I don't even have an x squared here, so it's kind of it's a fairly tame singularity, I think, as they go. And but anyway, we can work it out. So like I said, x equals to 0 is a regular singular point. If you divide this by x squared, right, you've got by 3. If you divide this by 3x, rather, it gives you, y prime prime plus 1 over 3x minus 1 over 3xy equal to 0. So the p would be 1 over 3x. The q would be minus 1 over 3x. X times p is 1/3, right? X squared times q is just, I think, x over 3. So of course 1/3 and x over 3 are analytic, which shows that it's a regular singular point. So you can sort through that. Okay, so then we're going to assume that our solution has the Frobenius form like this, which I could write like, why did I do that? I'm not sure why I did that. Why did I do that? I'm not sure why I did that. You can do that. Why did I do that? I don't know. Let's see. Curious. I actually did read these yesterday, so I just didn't notice that yesterday, and now I'm like, why did I do that? Anyway, let me go on here. So y prime, which one did I differentiate? I chose to differentiate this one, apparently, because I didn't ignore that. All right, fine. So there's y prime, and then y prime prime, right, would be the a sub n plus r minus 1, x to the n plus r minus 2, right? But I multiply by 3x here. So I brought the 3 in, and I added 1 to the power here. I guess my point is, oh, I know what my point is. We can meet in the middle. It's easier. See? So in this problem, it just so happens that multiplication by x on this term puts me to the n plus r minus 1 power, right? And the differentiation, of course, naturally goes to n plus r minus 1. And if I shift the index on the Frobenius solution, I can also have x to the n plus r minus 1. So then when I get to this point of plugging this, and that into that, then I've already got, So when I did this, I was more clever than I currently am. So, you know, these things happen. I mean, I was looking at some of the things I wrote this summer, and I thought, I knew this? Did I write this? I don't think Nathan wrote this. I think I wrote this. How did I know this? It's very disturbing, really. It's just been like a couple months, but man. Anyway, plugging it in gives you this. So you notice what I've done here is I've peeled off the constant term. Well, it's not a constant term, right? But the x to the r term, right? Which is coming from what? It's coming from, let's see here. I guess it's just coming from, right, exactly. And there's none of that here because why?
It's already.
Oh, okay, right. Yeah, I want to believe you, but I just doubt myself here. So your point is, if we look for constant terms, not constant, but x to the, oh, n equals 1.
Yeah.
But n equals 1 gives me a sub naught there. So it seems to me the minus y should give me a, it seems to me from this term, I do have I have an x to the r term, right? But it's just with the a sub naught. So I should get like a minus a sub naught from this, I believe. Shouldn't I? If I put n equals to 1, that gives me x to the r, right? So n equals 1 puts a sub naught here. So this term contributes a minus a sub naught, I believe. And you guys are saying this one does what? This contributes a, let me keep them. I may have already just simplified it in what we were looking at. I may not be wrong. I may just not appreciate why it is that I wrote what I wrote there. Let's work it out. Okay, it won't take long. So the minus y contributes what? So this is for x to the r coefficient, all right? Which is important because that's what decides the initial equation, right? For minus y we get, I think I was just saying what? Minus a sub naught, right? And from, what's the other term? Plus y prime, what do we get? To get this to be x to the r, what do we need to do? Put n equals to 1 again, right? But this time that puts this to be a sub 1 times 1 plus r, right? All right, so what's producing an x to the r term in this 3x y prime prime term? We put n equals to 1 again, right? And then what? So you guys tell me, what is it? 3a1 1 plus r times r. Okay, so all of these together gives us, what we got here? Minus a naught plus a1 times 1 plus r plus 3a1 r times 1 plus r. But there's also n equals 0 here, isn't there? And there's n equals 0 here too, isn't there? Right? Oh, you know what? So this is the coefficient of x to the r, right? But there's something below x to the r in this problem the way I set it up. What is it? X to the what? r minus 1 is what I should be looking at. That's the lowest rung on the totem pole, so to speak. Wait, I'm sorry, am I allowed to say that? I have 164th Cherokee blood in me. I'm allowed to say that. Let's see here. Fun fact.
So from that,
I don't really know that for sure. It's been told to me. Yeah.
so you're just looking for like a not in y prime.
I'm trying to equate coefficients of matching powers.
Right.
So like the lowest power that appears will give us the initial equation. So because of the way the general setup was arranged, it happened to be the x to the r coefficient. But the way I set this up, it ends up being the x to the 1 minus r coefficient. It's because basically instead of having an x squared here, we have an x, so it kind of shifts everything around a little bit. Anyway, look, let's just collect it. Can we get x to the r minus 1 here? Put what? N equal to 0. Oh, that's not, I mean, a minus 1 is not a thing. All right, so there is no term from this. There is no x to the 1 minus r term. Here, there is an x to the 1 minus r minus, I say x, 1 minus r, I meant r minus 1. R minus 1, n equals 0, right? So we got a sub 0 times 0 plus r from the y prime, and then plus what? Plus 3x y prime prime. So to get r minus 1, I put n equals 0 here. So I got 3a sub 0. And then that's what? That's r times r minus 1. So that implies that 3 times r minus 1 plus r has to be equal to 0. There's my initial equation. Stripping off the a naught. I knew this wasn't the initial equation as soon as I looked at it because it had both a naught and a1. It's one of the higher relation which intertwines the different coefficients. You notice that this is really different in structure than the problems, if you've worked the problems in your homework that I pushed back to Monday. Those ones tend to have a linking between like n and n plus 2, or there's another problem where you have a linking between n plus 2 and n minus 2, right? But there's some kind of, a lot of the problems you look at, there's some sort of interlinking between either every 2 or every 4 or something, or sometimes it's every 3, you know. But this, it looks like we're linking one to the next, and well, anyway, there's a lot of different things that happen, but that already looks different than your homework problems, I just say. Let me go on. So what is r then? All right, so I now believe it. We worked it out, right? 3r times r minus 1 plus r. It's legit. We've reproduced it. Oh no. And this one, right? So in this case, I mean, when you actually have unending when you have unending power series for the p and the q, I mean x times p and x squared times q, it's hard to actually do this step concretely like I did here. But because there's just one term in both of those, you can actually make this combination. What is it?
In that first equation there, shouldn't it be times x to the minus 1?
Yes, it should. I think we have earned that. Yes, it should. But then, of course, this over here, where did I start? I started at x to the r, right? So this is legit.
Yeah.
It's just that should be r minus 1. Yes, thank you. Very, very good. I need to fix this.
Yeah. I just thought about it.
Yeah, there.
Because some of the problems we had before, like if we had summations of like 2 of them were n equals 0, like 1 was n equals 1, like in this case, they just like, the way that I did it, I just like took out, I just plugged in n equals 0 for the first term, pulled that out summation, and then you do it that way, you get the same thing.
Oh, good. Yeah, I think that's entirely equivalent to what I'm saying. It's just, how you want to. It's like you want to rake the front yard and then the backyard. You want to rake the backyard and then the front yard. I mean, It's all the same stuff. Okay, so this being 0 relates the n and the n minus 1 coefficients, right? So you can put that equal to 0 and solve for a sub n, you get this, right? You guys see that? So add a sub n minus 1 to the other side. The coefficient here is 3 times n plus r minus 1. How'd I get a 2 here? What the what? What? I think I must have done some grouping. Yeah. Look at this. Factor by grouping. This is, you see you can factor out the n plus r. So here you've got 3 times n, 3n plus 3r minus 3, and then plus 1. So that gives me 3n plus 3r minus 2. So we do some factor by group, use distributivity to put this and that, together. Do you guys see this then, in view of that algebra? All right, and then, so this is what I was talking about. I think it pays off to do this without putting in what r is. You see, you could stop, once you find this, you could find out what r is, and you could do all of this with r being a specific value. But sometimes it works out that r has 2 distinct values and both of them matter. So if you do it this way, then you can just plug the r's in, and you've got recurrence relations for the different choices of r. Great. On the other hand, if you plug in r as soon as you find it, being impatient, then you have to do the algebra here 2 times with a specific, possibly ugly choice of r. See, because r could be something awful like square root of 17 divided by 3 or something. And then you'd have square root of 17 divided by 3, square root of 17 divided by 3 minus 1, square root of 17 divided by 3, it's awful. Of course, that problem would still be awful, but okay, so anyway, this initial equation gives us what? It gives us either r1 is equal to 2/3, and it gives us r2 is equal to 0. Okay, so we'll start with the index of 2/3. If we use 2/3, this becomes a sub n is equal to a sub n minus 1 over, so let's see here. Excuse me. What happens with 2/3? I get n plus 2/3, that's going to be this term. And then this here gives me what? I guess I just have to write it out if you guys want me to. Probably would be good for me to do that. Let me do that one. Let's see here. So n plus r times 3n plus 3r minus 2. And we're going to put r equals to, what did I say? 2/3. So we've got n plus 2/3 times 3n plus 3 times 2/3 minus 2. Aha, see what happens? And then the 3n multiplies to give me n times 3n plus 2. So distributing the 3 through to kill the fraction and moving the n to the front. And there you go. That's this. And then I just start doing hand-to-hand combat with the thing. So here's a1 is, let's see here, a naught divided by 1 times 6. Oh, yeah, what's 3 times 1? It's 3. What's 3 plus 2? It's 5. Yes, okay, so that's 5. Very good, very good. Oh, you've been practicing? Very good. Yes, I sometimes struggle. A1 over, let's see here. So I'm actually putting the numbers in the opposite order. So these are like 3n plus 2 times n. So 3n plus 2, that gives me 6 plus 2, 8 times 2. But then, of course, a1 can be put back to a naught over 5. So I get 8 times 5 times 2, a sub 3, 11 times 3. But then it gives you 11 times 8 times 5 times 3 times 2, 4, 14 times 4, 14 times 11 times 8 times 5 times 4 times 2. Anyway, so if you stare at this long enough, you can see that the pattern is 5 times 8 times 11 times 14 times 3n plus 2 n factorial. See what I'm doing? I'm pulling out this 2, this 3, this 5, and the next thing is there's a 6 from the, there's not a 6. The 5 comes from a sub 5. There's another 5 that appears at a sub 5, right? So I just keep pulling off these. Basically, I keep pulling off the n that appears here to create an n factorial, and the rest of them are just 3n plus 2, I think. Yeah, like this is 3n, this is 1, 3, 6 plus 2, 8, 9 plus 2, 11, 12 plus 2, 14, and so forth, all the way out to 3n minus 3n plus 2. So that's the pattern. Huh. I wonder if I put this on my Calc 2 test, how they would have done finding this pattern. You know, this would make a nice Calc 2 problem. I should put this on their final. Wouldn't it be funny if they were watching this? They don't watch their own course, much less this one. I'm just being silly. But anyway. I mean, I wouldn't watch my course if I was attending the classes anyway. Let's see here. I don't think. Okay, so anyways, that makes sense? I mean, so there is one of the solutions. This is the Frobenius solution with index 2/3. It's this thing. Look at that. That is a beastly thing. That's the 2/3, the cube root squared function. And then this is a sum of like higher root functions with that coefficient. Man. Oh, well, yes. I mean, it is generically true that if you know the answer, it makes the problem easier. Right? Yeah. I mean, guessing, well, and there's a more generic principle, right? The more clever you are, the easier a problem is. There's nothing more clever than knowing the answer to an integration, right? I mean, differential equation is no different, right? It's just extended integration. Okay, I digress. So R2 equal to 0, in that case, the recurrence is just this. So like if you put R equal to 0, so you get n times 3n minus 2, right? And it's kind of a similar pattern, right? This n is going to produce an n factorial, and that's going to produce a string of 3n minus 2 terms. So it starts out with 1, which is which is hard to see. And then the next one is 4. So it starts at like 4, and then 7, and then 10, to 3n minus 2. And then this n produces an n factorial in these as you look at it. Right? There's 3 factorial. Here's the 4 factorial, right? And so forth. And so there's another solution. All right? And that's our solution to this differential equation with a regular singular point by the method of Frobenius. This will be good. This will converge to this will be a convergent series. I can't say power series here. It's not a power series. It's something else, right? Because of this r being not an integer. But it does converge to a solution for positive reals. 0 is not included because 0 is a singular point. Now, if you wanted to get the solution for negative reals, it's not very complicated. What you do, just replace x with absolute value x, and that'll do it. I don't know. Maybe this. Well, if I do the squared, I guess it doesn't. Maybe this already works for. I think the absolute value of x to the 2/3 is x to the 2/3 though. So maybe this is a quirky problem where the formula works for positive and negative x. I guess it could happen. All right, moving along. So here I'm just remarking what I remarked earlier, which is that really this Cauchy Euler problem is the most basic kind of regular Frobenius problem. I think my next example actually has the details here. Yeah, check this out. It's kind of fun to actually churn through this method we just did in the case of Cauchy Euler problem. Like this, x squared y prime prime plus 3x y prime plus y equals 0. So that's regular singular point, p p not equal to 3, q not equal to 1. The initial equation works out to r times r minus 1 plus 3r plus 1, which gives you minus 1 2 times. And so if we look at the Frobenius solution with index minus 1, that gives us this. And if you plug it in to the differential equation, that gives you this. Collecting like powers so that everything's x to the n minus 1. I guess I already did that. But anyway, I can do, so I collect them, this. It gives us this relation n times n minus 1, n minus 1 times n minus 2 plus 3 times n minus 1 plus 1 for n equals 0. If you put n equals 0, you get 0 times a naught equal to 0. So, in other words, not especially surprising, this is saying that if you use the index, the initial equation solved. Okay, no surprise. But no condition for a sub naught is found. If you look at n greater than or equal to 1, if n is greater than or equal to 1, this is non-zero. Like, for example, if I put in n equals to 1, what does this give me? That's 0, but what's this? This is a sub 1. So n equals 1 gives me a sub 1 is equal to 0. When you plug in 2, this is like some number times a sub 2 equal to 0. So you get a1 equal to 0, a2 equal to 0, a3 equal to 0, a4 equal to 0, and so forth and so on forever and ever. The only thing that survives in the whole stupid Frobenius solution is the a sub 0 term. So the Frobenius solution with index minus 1 is just a sub naught times x to the minus 1, which of course is our beloved Cauchy-Euler solution from test 1, right? So like it's saying that in the case of Cauchy-Euler, the Frobenius series just truncates to the first term. So, and likewise, this other one, of course, we get the log x over x. Now that we don't quite appreciate yet from the method of Frobenius, right? Somehow the method of Frobenius also has to run into this log stuff, right? Let's try to talk about that. But before I talk about this pesky log issue, which is, a little bit sneaky, let's look at x squared. This one. All right, so try to pick up the pace a little bit here so we get through it today. I could talk about this for, 2 weeks, but I think if I talk about it for about 2 days, you'll understand as much as you're going to understand from me talking about it. Then you got to do some problems. And it's probably better for me to spend much more time talking about systems of equations in here than I have on the syllabus. So I'm basically planning to expand that discussion for you guys. And this I'll try to keep nice and lean. Because again, I don't think it helps to have me talk about it much longer, Okay, so if you look at this problem, the initial equation ends up being, where's that stupid thing? Where'd it go? Right here. R times r minus 1 plus r plus 4 equal to 0. All right, that simplifies to r squared plus 4 equal to 0. So we have the index plus or minus 2i in this case. This calculation's still all legit. It's just we now should think about the coefficients as being complex coefficients. We'll expect to find one complex solution. And because this is a linear differential equation, if you have a complex solution, the real and the imaginary part of the complex solution will be separate real solutions to the problem. So if we've got a complex exponent, it's actually kind of a blessing. It means that we find both Frobenius solutions from just looking at one of the indices. Because both of these indices, plus or minus 2i, they'll produce the same data. Now, because we have no love of minuses, we'll work with the 2i term rather than the minus 2i term. But you ever think the term "it just got real" should be replaced with "it just got complex"? I think it might be a legitimate point to make. Let's see here. Anyway, so here we have r plus 2i, r minus 2i, and that was the recurrence relation we found. And so when I look at that, when I plug in 2 plus I, it gives me this. All right, so I got to do some complex arithmetic. This is n squared plus 4ni minus 4 plus 4. Well, those cancel. Woohoo! And that gives me n squared plus 4ni. Now, what I'm doing is I'm multiplying by the, ignore the cursor, curse the cursor. So here, n squared minus 4ni, n squared minus 4ni, well, that's, I'm multiplying by the conjugate of the denominator as to make it into Cartesian form. In other words, to put the I upstairs. And there's the, sort of the Cartesian form of the recurrence relation. And so that's convenient for me to actually recurse on, because that will produce these guys. So like A1 is A sub naught times 1 minus 4i over 17. A sub 2 would be A sub 1 times 2 squared, which is 4, minus 8i over 4 times 4 plus 16. That is 80. And that is a multiplication I have to do, right? So 1 times 4 is 4. 4 times 8 is 32, but so I get 4 minus 32 is minus 28. The imaginary parts, I get minus 16i, minus 8i, that's a total of, hey, try that again, minus 16 minus 8 is minus, hey, man, try that again, 14 minus, I got 24 here. Aw, man. Well, that I think should be a 24. I don't see, do you guys see anything that I have unseen? I think that's supposed to be a 24. Okay, so anyway, you know, my stupid arithmetic mistake aside, I'm not going to find the general recurrence. I mean, you could fuss with this and try to find a general pattern or something, but I'm going to content myself with just the first few terms here. So this is the a sub naught times x to the r, but r is 2i. Here's 1 minus 4i over 17. Again, this is supposed to be 24, right? And so what I do then is I bring out the x to the 2i out here, right? And so that puts a 1 from that, right? And this x, that becomes x times x to the 2i, right? So that puts an x here, which brings it down here. This one, again, x squared times x to the 2i, which brings me this x squared times 28 over 17 times 80. Then I'll collect the I terms. So like here ix minus 4. So there's the minus 4x 17 and the multiplication by I. Over here, again, that should be a 24. So minus 24 over 17 times 80, the x squared. I've brought out the I here, and of course I factored the x to the 2i out there. This gives me no love of writing these things, so I call this A and I call this B. Your book might do the same. I'm not sure if this notation was his. Anyway, it's a notation. You could call this thing A and call this thing B, right? Then this we talked about before, right? What's that? That is e to the 2i times log of x, which is, what was it? It is, well, here it is. Cosine of 2 log x plus I times sine 2 log x. That's what x to the 2i is. And so, you know, put n equal to 0, x to the 2i is just this business. So I've got x to the 2i is this times that. And then what I do is I rewrite my solution. All I'm doing is multiplying this stuff out as to present the real part of it and then the imaginary part of it. So the real part is coming from a times the cosine term in here minus b times the sine term in here. And then the imaginary part is coming from the cosine term in here times b, and then the sine term in here times a. Both of those pick up a coefficient of I down here. And then, so the story is, that is the one Frobenius solution, and that is the other Frobenius solution. Keep in mind that this A and B are these awful unending power series is generated by by the recurrence. And there you go. That's how you solve a complex Frobenius problem. Just the same, but you got to work with the complex recurrence, and you got to split off. You got to do this, collecting real and imaginary parts at the end. So it's kind of a hard problem. So the calculation which follows here differs from our initial example in one main aspect. I put in the exponents before I look for the recurrence relation. I said it turns out that the method of example 4.42 is a far more efficient method of calculation, but I'm going to leave this slightly clumsy calculation to show you the difference. Oh, in other words, I was too lazy to retype this, but I guess we'll suffer through it. So my point was, this is what happens if you put the index in and calculate with it. So here, we have x, y prime prime plus that. So that's a kind of ugly thing, but not too ugly, right? It's so much worse if this is like e to the x. Because then you have an unending power series, every order. It's just so much worse. Anyway, so the exponent, the initial equation is r times r minus 1 plus 3r in this case. And that yields r times r plus 2. So the exponents are 0 and minus 2. This is worrisome. Generally speaking, if the exponents differ by an integer, then there's no guarantee that the Frobenius solution is going to work in the second case. Like, it'll give you one solution, but it may not give you a second solution. It's necessary to add a log term. But it so happens not in this problem. So this problem is kind of a quirky problem in the sense that it doesn't require the introduction of a log term, even though the indices differ by an integer. Anyway, so you run through the usual thing. But I'm going to look at the 0 index, which gives this just as a power series, right? And excuse me. So, and then I just multiplied this out, right? And then, so this is the terms of order, the constant and the linear terms in x out front. N times n minus 1, that's that series there. And then there's 3n from that one. This one is the x squared y prime, so the y prime would give me x to the minus 1, but then x squared changes it to xn plus 1, but the differentiation leaves the n out there. And let's see here. Okay, so these, I've got n plus 1, n plus 1, n minus 1, n minus 1. I gotta change something here. So I'm gonna make j equal to n minus 1 for the first two sums. I'm gonna make everything become n plus 1, I think. Oh no, I just meet in the middle. All right, well, great. So I'm going to let j be n minus 1. I'm going to let j be n plus 1. Do these all start at the same place? I think they do. N equals 3 gives me x squared. N equals 3, x squared. N equals 1, x squared. N equals 1, x squared. So I've peeled off the terms which have a different starting point for these sums. They're up here, right? Now I've written this so that all of these are from x squared to infinity. So when I make the substitution of j n minus 1 and j equals n plus 1, the whole thing starts at j equals to 2. All right. Yeah, go for it.
Why is it that if the R1 and R2 differ by
Yeah.
why is that problematic?
I don't know. We can't see it from this example. I'm gonna have to hold off on that, but it matters. Let's see if I can't find an example in the book here. So let me just run through this quick so we have time. That is a good question, which I'd like to answer. Anyway, so then you've got this is the recurrence. This is going to give you a recurrence relation. And what is this force? This force is a1 to be 0, right? And this is forcing A2 and A0 to be linked, right? This looks like it's got a sort of a duplicity. It's linking J minus 1 and J plus 2. So the fact that means that the even and odd coefficients are going to be linked. The fact that this forces A1 to be 0 means A3, A5, A7, A9, so forth and so on forever and ever, 0. And then the even coefficients are going to be linked in some kind of complicated way. In particular, here they are. So it works out that you have an even power series solution as it happens from the 0. I mean, this is a quirk of this example is that the Frobenius solution actually is a power series solution. But like I said here, we're missing a solution then, right? So where's the other one? Well, the other one comes from looking at the index of minus 2 in this case. And this one's kind of quirky. The minus 2 one, mostly, it kind of, when you look at it, you get A1 is 0, no condition on A naught. This forces, no condition. This one forces A3 to be 0. This one links A4 to A2. This one links A5 to A3, A6 to A4. And if we had been going through the other case more slowly, you'd recognize these as being, but you notice the A3 is 0, so that's 0, right? So the evens will be linked. The odds are all 0. A sub 0 is sitting there by its lonesome. So let's summarize what happened here. So the second, the index, what was it? Index minus 1, was it? I've forgotten already. Index minus 2, rather. Works out to this. And there's also the A sub 0 term over here, A sub 0 over x squared. Okay? But if you look at all these, and you factor out the A2, you've got this. But that's exactly just a relabeled version of the first solution. Like this is exactly what we got from the R equals to 0 index. This is the 0 index solution. So a copy of the 0 index solution has appeared in the minus 2 solution. That starts to answer your question. When they're linked by an integer power, you get some kind of overlapping between the solutions to the different indices. And if they overlap too badly, then you just get back the first solution again, which means you haven't found a second linearly independent solution like you need. Now it happens here that doesn't happen because you've got this, thankfully, a sub naught x to the minus 2 term, which gives me a second linearly independent solution as it happens. It has a Cauchy Euler solution, this problem does. So we got lucky here. I'd like to find you a more complete example. Let me just run the clock out. I mean, sorry, I'm not running the clock out. Let me do this right quick. The repeated root technique. This is actually a slightly better derivation of the differentiation with respect to the parameter thing I did for you guys the other day. So suppose you have a double root in the initial equation, right? Well, let's see here. Here's I think this is a derivation for the Cauchy Euler problem. I guess actually I'm just doing the constant coefficient here at the moment. So suppose you've got a repeated root constant coefficient differential equation which would have the form d squared minus 2 lambda 1 plus lambda 1 squared y equals 0. Suppose that y lambda x equals e to lambda x. Then if you look at L of e to lambda x, what do you get? You get lambda squared minus 2 lambda 1 lambda plus lambda 1 squared e to lambda x, right? And if you look at that, that's lambda 1 minus lambda 2 squared e to lambda x. So if I look at y2 as partial lambda, y lambda e to lambda x, I can show that that's a solution because L of y2 would be L of this, right?